Okay, this is problem 458. It's on page 180. Water flows through a shower head steadily at a rate of 10 liters per minute. An electric resistance heater placed in the water pipe heats the water from 16 to 43 degrees Celsius. Taking the density of water to be a kilogram per liter, determine the electric power input to the heater in kilowatts. Okay, so let's do the first part to begin with, and then we'll read the second paragraph and figure out that. Okay, so initially, what we've got is a system. I'll sketch it over here. Actually, let me move it just a bit. Let's see, I guess we'll go down here. So there's an electric heating element. This will be section 2. Coming in, I'll call section 1. Now, the cold water comes in at a temperature of 16 degrees Celsius, density a kilogram per liter, and volume flow rate 10 liters to L per minute. Okay, I should have moved that, but we'll take care of that later. The temperature coming out of this heater is 43 degrees Celsius, and the whole point of this thing is to provide hot water for your shower. Here's the shower head. Here's the nice warm water coming out of your shower head. Okay? We're supposed to find the electrical power rating. Why would we care about the electrical power rating of the heater? If we want it to be hotter, just throw more electricity into it, right? Why? What difference does it make? Why would we care?
We can make it too hot.
We could make it too hot, that's true, but we probably have some kind of controller, so if the temperature goes up too high, we'll stop putting quite as much current in. Why else would we care? This is something that a lot of people don't understand. A lot of people will take those little splitters for electrical outlets and they'll plug in one, then they'll plug another splitter into that splitter. And it's kind of the joke, right? That you just make this tree of splitters that comes out. Well, why is that a bad idea? Because that outlet can only provide so much power. If the power that you're trying to draw from the outlet goes above the rating of the outlet and the rating of the wire, one of two things is going to happen. Either your fuse or your circuit breaker is going to blow, hopefully, or it's going to catch on fire. Right? Those are basically the two options. If you've got the penny in the fuse instead of the actual fuse, you're probably going to start a fire. If you've got an oversized breaker and an undersized wire, you're probably going to start a fire. Neither which are good, right? In fact, most fires in homes are caused by electrical problems. So what people don't seem to understand is that the power coming out of the wall, while it is powerful and there's a decent amount of it there, there's only so much of it. Okay? So what do you have to do if you want to put a whole lot of power into something? By the way, this is going to take quite a bit of power to run. What do you have to do? Well, you have to provide a large enough breaker and a large enough wire to do it. Now, did you know that when you buy wire, you usually buy copper wire, right? Okay. And as that copper wire size gets bigger, you know what happens to the price of the wire? It shoots up through the roof, right? And so why we care about the amount of power this draws is because that's going to help us determine what size wire we have to run. Now, of course, it'd be a good idea to run this off of 220 instead of 110. Do you know why? Because to get the same amount of power out of 220, you need half the current you do from 110. Okay? So basically, you can get the same number of watts out of 220 that you do out of 110 with half the current, half the I, half the amps. Okay? And the reason that that's important is because wire, copper wire, its limiting factor is the amount of current it carries, not so much the voltage. If you ever install Romex, which is wire for a home, and you look on the side what's printed on it, it usually says 600 volt. You might be confused and say, well, I'm putting this on a 110 outlet. Why would it be rated at 600 volt? 600 volt is the potential that those wires can carry versus each other without arcing out. Okay, the voltage is really not what's so important. It's the amount of current going through it. So it'd be a good idea to run this off of 220 or even more if you could, right? Of course, in residential, that's not really an option. Okay. You guys may remember the movie, I think Tim Allen was in it, but I can't even remember what movie it was, where he was acting like he knew what he was talking about. He wanted to get a garage built, so he had a contractor come over, and he said, so the contractor saying, so you want to wire it with 220 or what? And he said, 220, 221, whatever it takes. Acting like he was macho and knew what he was talking about. But anyway, so 220 is probably what you wire this with, but we still want to know the power draw, right? If this is a temperature that's comfortable for showering, and notice what we're doing here, we're getting rid of the water heater, right? We're just eliminating the water heater. This is just hot water on demand. Why would that be a good idea?
It reduces, the ones that they use now are really efficient. You know, they have the gas heat, and then they heat up real quick. You don't have to store hot water anywhere.
Right.
So there's pros and cons to both.
Well, the main problem with having a big tank full of hot water somewhere is that heat is going to leak out. Does that make sense? You're going to lose thermal energy constantly. In fact, remember we had a homework problem. What was that? What chapter was that? 4? Right, with the water heater problem, remember that? Okay. The water heater problem, you calculated the loss and you calculated the cost of that loss. So the idea here is we're not going to have that loss because we don't have a big tank of hot water sitting anywhere. Okay. But the trade-off is we got to pay for big copper wire or relatively large ones. So let's see what that's going to cost. Let's see what that would require. Okay. All right. So what I'm going to do is take my system like this, okay? Because basically I've got electrical power flowing in here. I've got some energy carried in this way by the water, right? The water's not at absolute zero. If it was, it wouldn't flow real well, okay? It's bringing in energy. So there's energy being carried in by this water mass coming in, but there's energy also carried in by the electricity, and then energy being carried out of the system. Does that make sense? So this is kind of like the duct flow that I showed you. Remember that device? Okay. And it wasn't chapter 4, because chapter 4 is the one we're working on. Where was the water heater? Was that chapter 8?
Last chapter.
It was Shell, I thought. 13?
I think it couldn't have been 13, because 13 was heat exchangers. It was either 8 or 9, probably 8. Anyway, you remember it. Well, hopefully you did that homework, right? Okay, so anyway, so what do you think I'm going to do to analyze this?
You're going to show the energy in versus energy out.
Energy in versus energy out. We call that a
Energy balance.
energy balance. That's all it is. It's just accounting for it. It's kind of like accounting for money, where it comes in and where it goes out, right? That's all we're doing with energy. So the energy balance. Let's start from the first part of the energy balance. This is going to be a steady flow energy balance, right? Because there's no accumulation or depletion of energy in the control volume. It's at steady state. So let's write down the energy balance. Q dot less W dot equals M dot, and let's put in all the stuff that can change. So what I've said here is there can be a heat flow rate and a work flow rate into or out of the system. I'll figure that out in a minute. But then there can be mass flow into and out of the system. In fact, there is one stream in and one stream out. That mass flow can carry energy in a couple different forms. What forms can it carry it in?
Thermal.
Thermal, good. What else?
Kinetic potential aren't worth
Kinetic potential aren't worth it. We'll end up crossing those off. But there's one more that's important. Do you think the system's pressurized?
Yes, it is.
Yes. And so there's also
Pressure.
P,
the side
pressure
effect
times,
of thermal.
P times V. Remember PV, flow energy? Okay, we put PV, flow energy, with the thermal energy, and we call that enthalpy. Okay, so when I write H2 less H1 here, I'm referring to not only the thermal energy, the motion of molecules on the molecular scale, but also the PV part of it, the flow energy. Okay. So then plus, we can do it this way. We'll save ourselves some time because you guys know we're just going to cross those two off anyway, right? We could expand them, but in this particular example, kinetic and potential energies will not be used. Now what about any heat flows? I mean, the water's coming out warmer, so is there any heat flow? How many people want to say yes, there must be some heat flow? You want to say it, don't you, right? Because the water heats up, but there's not. There's no heat flow. Because look at the system that I chose. We've got electrical work going across this. The heat, if you want to call it that, is generated within this coil, which is inside of the system. Now, if I had made an energy balance and had a system that did not include that coil, then we'd have heat flow across the boundary, right? But basically, the electrical work just gets transformed into thermal energy. That's all that happens, okay? So this one's 0. But the electrical work is not 0. Now, is the work, since it's going into the system, is that a positive thing or a negative thing? It's a negative thing, that's right. So, it is negative coming in. Make sense? Okay, remember, work flowing out is positive, work flowing in is negative, and we'll get rid of the stupid sign convention once you get to 320, okay? All right. Because it's just confusing. The whole reason for it is because of boundary work. But anyway. So that equals m dot H2 less H1. And let's simplify this down just a little bit. The electrical power then is m dot H2 less H1. Basically what the electrical work does is it changes the energy of the flowing stream. That makes sense. That's easy. Now how about that enthalpy change? How are we going to calculate the enthalpy change? For that matter, how are we going to come up with the mass flow rate? Well, the mass flow rate could be written as the density times the volumetric flow rate. That would take care of the mass flow rate. And then delta H, how do we approximate that with a change in temperature?
CP delta T.
Cp delta T. Do we need to worry about any enthalpies of evaporation or anything like that? Any HFGs, are we worried about that?
Doesn't change phase.
It doesn't change phase, that's right. It comes in as a liquid and leaves as a liquid. If it changes phase and comes out at 100 degrees Celsius, we've got worse problems than the side of a copper wire if you're standing in the water. Okay? So yeah, it doesn't change phase. That's why Cp delta T will account for all of the change. It's all a sensible energy
Wouldn't be
change.
much of a shower either.
What's that?
Wouldn't be much of a shower either.
No. It'd be a steam bath. Okay, so let's see. The density is a kilogram per liter. We've got 10 liters per minute flowing, so the liters go away. The heat capacity of water, you'll probably get that memorized eventually, 4.18 kilojoules per kilogram per degree Celsius or Kelvin. It really doesn't matter. We're talking about a temperature change. Temperature leaving, 43 degrees. Temperature entering, 16. Those are degrees Celsius, which will cancel nicely. And what we'll have is just kilojoules per minute. Now this is 1128.6 kilojoules per minute. That's the power flow rate we'd have to have. Now, if you're going to go and buy some electrical wire, you'd probably like to have the current draw. To get the current draw, you'll need to know the power flow rate, and that would be in kilowatts. So just for fun, let's go ahead and calculate the amp draw on this, okay? We'll calculate it at 110 volts and at 220. This is not part of what your author asked us to do or what I've got on my solution, so I'm going to need some calculator help. So let's go ahead and change this a little bit, because a kilojoule per minute is not a kilowatt. A kilojoule per second is a kilowatt. So 1 minute is 60 seconds, and now we will have kilowatts instead. So take the number I gave you, divide it by 60, and what do we have?
18.81.
18.81 kilowatts. Is that a lot? Your house on average draws 1 kilowatt or so. Okay? This is quite a bit actually. Let's find out what the current draw would be. Let's start off with 110 volts and see what happens. So do you know that power, in this case electrical power, is equal to the multiplication of amps times volts? Okay, so we can use that equation essentially and say, well, if the voltage is known, then the current would be the electrical power divided by the voltage. So the electrical power is 18.81 kilowatts. And by the way, do you guys know, before we do this, do you know what standard breaker sizes are for 110? What's the most common?
30 amps?
30 amps is pretty big.
Yeah.
15 amps average, it's normal. I've never seen a 10 before, but I suppose you could get one. 15, 20, those two are the most common ones you see. You can get a 30 amp breaker, but you better have pretty good wire to put on it. Okay? So 15 to 20 amps is normal for 110. So let's divide this by 110 volts. Now we need the power in watts instead of kilowatts. So this is 18,810 watts. So divide 18,810 by 110. What do you have for the current flow?
171.
Just 171 amps, that's all. Surely, Mr. Inspector, you could pass that on my 15 amp breaker. Okay, do you see the problem here? They're not going to work real well, okay? So obviously 110 volt is not going to help us. Let's try the current at 220 volt. Now 220 volt current flow breaker sizes basically are usually quite a bit bigger. You can get 30, 40, 60 amp.
85.5. It's just
5.5 amps. That's still a big 220 breaker. Okay, do you see a problem here? This is gonna be expensive. By the way, your clothes dryer doesn't draw that much. Usually a clothes dryer sits on I think a 60 amp breaker or so. Okay, so this is a whole lot more. And it actually makes sense. Your clothes dryer is just trying to evaporate off a little bit of water. Here you're trying to heat up quite a bit of water. Okay, so the power draw is here. So there's a problem here, right? This won't work very well. And you could do it. You can get 100 amp 220 breakers, but the wire you have to put on is pretty expensive. So if this is just one faucet, one shower in your home, and you're gonna put these all around your house for each individual outlet, you've got a problem, right? Not gonna work real well.
Just need a lot of 440.
What's that?
Just need a lot of 440.
We need 440 somewhere, there you go. Have to have the electrical guys come and install a custom transformer for us, that's all.
Is this
Face converter switcher.
similar to how like one of those mini air heaters work? Because I have like one of those ones and it pops breaker almost every single time.
That's right. Anything that takes electricity and converts it into heat, usually you need so much thermal energy that it's gonna draw a whole lot of electricity. And so those are really expensive to run. My house came with two of those. It came with 2 bathrooms. They were both kind of nasty. I ended up remodeling both of them. I took one of them out, the bathrooms that is. I actually took both of those heaters out. Okay, and I thought, you know, some of my family would probably really like it if I would keep these because you could go in when it's coolish, turn it on and feel nice and warm. Yeah, but they're gonna draw a lot of power. They're gonna be very expensive. So instead, what I'm choosing to do, I put in tile floors, and I'm eventually gonna, during the wintertime, heat the tile floors so that you get radiant heat transfer, which will actually feel better and yet not be as expensive to run.
So are clothes dryers actually the most, I mean, obviously they're,
Are they the worst out there?
well, are they the worst, but is there a better way to do it, but we just don't do it that way?
Oh,
because
yeah, sure.
We've been doing clothes dryers for so long.
Yeah, it's sun
Other
outside.
than that, I mean, like appliance-wise though.
Appliance-wise, is there
Yeah.
something different? Not that I know of. The problem is you want the water to come off quickly, and if all you do is you blow air through it, it's gonna take quite a while for that water to evaporate and come off.
So the problem is
So
you
you
want
need
it
the
quick.
air.
Not-
The problem is that we want it quick, that's right. Yep.
What about convection ovens?
Convection ovens, you're talking about for cooking food or for drying clothes?
Well, could we do both?
Your oven.
Well,
Can I get rid of my dryer?
Basically, your dryer is a convection oven, okay? But it's just not as high power. What about convection ovens? The key thing about an oven, even though an oven is on a 220 breaker and it can draw quite a bit of power, it's well insulated. So you're not just drawing air through it constantly like you are a dryer. And so what you need to do is get it up to temperature because you need the reaction in the food to take place, right? Whether it's cooking meat or baking a cake or whatever. So the amount of energy you have to put into the oven's not as high as you might think. And a convection oven's even better because it more efficiently transfers the heat to the food directly, so it doesn't take as long to cook, so you have less loss. Okay, plus you get your food quicker.
So our dryers take up so much power because they're poorly insulated?
Well, they're purposely not insulated. You're blowing air through it.
Oh, okay.
Right.
Because you're trying to get them, okay.
Right, you're trying to pull the moisture out. Now, really the device, though, that costs you the most is heating and cooling, because you're trying to heat and cool the whole house. The second device that costs you the most is the water heater, because water is fairly dense and it takes quite a bit of energy to heat it up and cool it down. So you usually want to heat it, so that's where. This is a good discussion. Anything else?
So how do they make like, they have on-demand water heaters, how do they make them work if they need so much? Is it because they're gas? They're obviously.
Well, gas would be much easier, because it's
Yeah.
much easier to get the amount of power you need with a gas flow rather than electrical flow. How do they do it? Well, they can't do this,
No.
not at this rate.
Yeah.
Let's see. The reason for hot water heaters is that you can run a fairly small wire and basically pour energy into the tank over a long period of time. Okay, and that way then that water can quickly be released for your shower, and then it's got plenty of time to build back up. So it's basically a capacitor is what it's like. It stores thermal energy instead of electrical energy. All right, so this is a problem, but here's a potential solution. Number one, we could cut down the amount of energy we use because this is going to cost money, and maybe run a smaller wire to this heater. Okay, here's the idea. What if instead of doing this is the next part of the question. What if instead of doing this, by the way, let's write down the answer. For A, the electrical power is 18.8 or so kilowatts. Okay. What about instead? What if we were to connect? Let's change this. Let's make this state 4 instead of state 1, and let's add a clever idea here. Let's take the incoming water that has to be heated up, and let's run it through a heat exchanger. So now, basically what we're going to do is move state 1 back here, where the water still comes in at the temperature of 16 degrees Celsius, because it's coming from the city, right? There's no way we can change that. Still has the same density, kilogram per liter, and still requires a volume flow rate of 10 liters per minute. Now here's what we're going to do. Instead of taking all this water that's just going down the drain and throwing away that thermal energy, we're going to recover some of it. So what we're going to do is in the shower pan, where the drain comes down, we're going to take this stream and run it through the heat exchanger, right? So we'll pull some heat out of it to go into the cold water. Okay. Now if we do that, that'll be nice, and I guess I should go ahead and read the problem statement, and then I'll continue this. In an effort to conserve energy, probably conserve the cost of the wire, it is proposed to pass the drained warm water at a temperature of 39 degrees Celsius through a heat exchanger to preheat the incoming cold water. So basically what they're saying is you're taking this water, you spray it all over the place, it's going to cool down some. It touches your body, it touches the surrounding surfaces, it touches the air, it's going to come down. So it's going to come, let's say, at a temperature of 39 degrees Celsius, and I will call that state 3. Okay, so the temperature at state 3 is 39 degrees Celsius.
You can't do this with a bath, so wouldn't that make it much more expensive thermally?
Can't do this with a bath, why not?
Because you hold the water, you don't let it go through an exchange.
Oh, with a bath, oh, I see. Yeah, there you're gonna have to heat up all the water, so what you'll just have to do is have a low flow rate in the
That's
bath.
different.
Yeah. So, let's see, where were we? Oh, yes. So the problem statement, if the heat exchanger has an effectiveness of 50%, you guys know what effectiveness means because you just studied chapter 13 and you're going to have an exam over, so you know exactly what that means, right? Okay, good. That is, it recovers only half the energy which could possibly be transferred from the drained water. Determine the electric power input required in this case, and then if the cost of electricity is, they have 8.5 cents per kilowatt hour, we're going to change that to 10 cents per kilowatt hour, which is still a little bit low these days, but we'll change that part of the problem. Determine how much money is saved during a 10-minute shower as a result of installing this heat exchanger. Okay. Let's see, let's get rid of our calculations here because we're done with them. All right, so there's our effectiveness. We've got all of our states labeled. And notice we don't know the exiting temperatures here. We'll have to figure out the temperature here at state 4. This is all just state 4, okay? So we need to know that temperature. That way we could calculate the new power input, right? Because basically this warm water is going to heat up the cold water a little bit, and we won't have to pay for that extra. So there's going to be heat transfer from the hot stream to the cold stream. Now, let's wrap our heads around that effectiveness. What does that really mean? Well, that means that only half, because the effectiveness is 50%, only half of the maximum heat transfer rate is going to be the actual heat transfer rate. So do you remember how we did that? Well, we had effectiveness multiplied by C min multiplied by temperature of the hot stream in less temperature of the cold stream in. Remember that from chapter 13? Okay, this was Q dot max. Okay? Now, C max and C min are going to be the same thing for all practical purposes, because remember C max and C min, how do we calculate those again? What are they?
C equals minimum or maximum.
Well, you're thinking of the capacity ratio, C min over C max, but to get the capacity rates themselves, how do we do that? One of those things you'll want to write down for the exam because you'll need to know this one pretty well. It's just the mass flow rate multiplied by the heat capacity. Okay, it has more to do with how much capacity the stream has to, or sensitivity to energy flow to and from the stream.
What is the T's? Is that the difference?
This is the temperature of the hot stream coming in, which is going to be 39 degrees, and the temperature of the cold stream coming in, which is going to be 16 degrees.
Okay. Alright.
So do you,
What was the question that you were asking with the?
what I was asking was, how are we going to get this C min? Well, we're going to multiply the mass flow rate times the heat capacity to get it. Now,
Yeah.
which side, which one's the max and which is the min? Well, think about it. The water that's coming in here basically comes back out here, right? So the flow rate and the heat capacity are essentially the same. Okay, yeah, there may be some extra dirt, there may be a little bit of soap. We're not worried about that difference, right? So C max and C min are basically the same thing in this problem. There's just a capacity rate. And the way we'll calculate it is the mass flow rate times the heat capacity. Now that's just the density times the volumetric flow rate times the heat capacity. And we already did this, or part of it, just a minute ago, but let's do it again. There's 1 kilogram per liter and 10 liters per minute and 4.18 kilojoules per kilogram per Kelvin. Okay, so let's see, the liters go away, the kilograms go away, and anyway, numerically this comes out to 41.8 kilojoules per minute per Kelvin. So basically what this is saying is you got to put in 41.8 kilojoules every minute to get this stream to come up by 1 degree Kelvin. Okay? That's all that it really says. So the actual heat transfer rate we can now compute because it's just 50% of that, right? So 50% of 41.8 kilojoules per minute per Kelvin is, and I'm sorry, that was the, I forgot the temperatures. That was the minimum capacity rate. I forgot to multiply by the temperature. So 43, not 43. Temperature of the hot stream is 39. Temperature of the cold stream is 16. There we go. Okay, so the actual heat transfer rate then comes out to 480.7 kilojoules per minute. Now remember the number we had before? The power rating was 1128 or so kilojoules per minute. We're saving 480 of those now. We've almost cut the requirement in half. That's pretty significant. Okay. So basically, this Q dot represents energy saved, right? Because this is energy that does not get just thrown away. So couldn't we calculate the value of this? Now the shower is a 10-minute shower. So the total amount of heat we need for the shower will be the heat flow rate times the amount of time that elapses, right? If we need 480, if we save 480.7 kilojoules every minute, we do that for 10 minutes, we've saved, what, 4,800 and some odd, right? We calculate that, so 480.7 kilojoules per minute times 10 minutes worth of shower gives us, let's see, saved amount of, well, we can do this in our heads, right? So we're going to save about 4,807 kilojoules. Okay. Now, how much is that worth? Well, grab your calculators because I used a value of 8.5 cents per kilowatt hour. But we need kilowatt hours. Now, you have to be careful. Kilowatt hours are a unit of energy. Kilojoules are a unit of energy. Okay, both of those are units of energy. Kilowatts is a measure of power. Now, a kilojoule is not equal to a kilowatt hour. They're different sizes. We don't need to add time in there. They're just a conversion factor. It turns out if you look in the front cover of your book, you'll see that 1 kilowatt hour is 3,600 kilojoules. Okay? So all we have to do is divide by 3,600, and then if every kilowatt hour costs us $0.1, because that's what 10 cents is, then we can figure out how much money we save here. Okay? So grab your calculators, take 4,807, divide it by 3,600, and then multiply by $0.1. So let's see what you get.
8.5 cents.
How much?
8.5 cents. Oh, you changed it to 10?
I know, yeah, I changed it, because today's rates are higher than 8.5
Oh, okay.
cents.
Got 13 cents.
13 cents. Do you think we could advertise this heat exchanger at Lowe's for a couple $100 and say you get to save 13 cents every shower?
It adds up.
Hands up, come on, buy it. Oh, and by the way, you gotta clean it out every now and then because hair and junk gets stuck in it. Right? That might be a problem. Might be a hard sell. Here's a better way to sell it. You might be able to say, look, you can have hot water on demand and you won't, you can save $100 on this wire. And then you'll save quite a bit, or you'll save money every time you shower. And then you can figure out, if you shower once a day, you save 13 cents, or you use a price of 15 cents per kilowatt hour, which is probably even more realistic. Okay? Then you can figure out the savings are gonna eventually pay for this thing. It's gonna take a little while. But hey, you get hot water on demand. What's
Did we
that?
decide that the kilojoules to raise the water up to that heat would, that's with the heat transfer?
Yeah, this is with the heat exchanger. Remember the number before was 1128 or so?
Yeah.
Okay, we're gonna save 480 of those, so it's a little over a third that we're saving.
It's still a lot though.
It's still a decent draw, but basically we could use a 60 amp breaker with 220 and the wire wouldn't be as bad as using 100 amp service.
Okay.
Okay, so that's where the savings. Now the other place that the savings comes in, there's more savings than this. This looks small, but you know what else you could save? You don't have to have the water heater. Remember the water heater that loses heat like crazy? Okay, that's where a lot of your savings is going to come from. That's one of the main reasons for doing this in the first place. Okay, so of course marketing is going to factor all that in together and make this number look big, right? You can't afford to not buy this. Okay. Any questions, comments? Okay, thank you.